Okay, so now we're going to look at practice problems for the gas laws. And so in the previous video, we looked at the gas laws, and so now we're going to look at a couple of practice problems. The practice problems that I'm referring to come from the back of the textbook. There's an appendix in the textbook, and so if you turn to page R115 at the very back of the textbook, you'll see for chapter 11, which are the gas laws, there are some problems. And we're going to be looking at 237 through 247 today, and these problems will go on maternity leave, page 104. Our notes went on 105, and so our practice problems will go on 104. Okay, so let's just kind of remember what we covered in our previous video. We talked about the gas laws, and we saw Boyle's law at constant temperature. We saw that inverse relationship. Charles' law, we saw the direct relationship between temperature and volume, and then for Gay-Lussac's law, we saw the direct relationship between pressure and temperature. We remember that our units between pressures or between volumes, between temperatures have to match, and our temperatures for Kelvin must always be in our temperatures must always be in Kelvin in the equation, but we can convert in or out of Celsius using the equation that Celsius plus 273 equals Kelvin. Okay, so those are our three equations, and we know the ones mean the initial conditions, the twos mean after the change. All right, so one of the things that I want to show you is I just want to show you this little kind of like seesaw thing. So if we write pressure, volume, and temperature, we can use it to help us remember the relationships. So if I talk about temperature being constant and I hold it at temperature, when the pressure goes up, you'll notice that the volume is going down. But if the pressure goes down, the volume goes up. That's that inverse relationship. But if we look at, say, Charles' law, where pressure is constant, if I hold it at pressure, when the temperature goes up, the volume also goes up. And when the temperature goes down, the volume also goes down. That gives us that direct relationship. And finally, when I look at constant volume, if the temperature goes up, the pressure goes up. If the temperature goes down, the pressure goes down. And so that's just one way that we can kind of use that PTV, and we cover up the thing that's constant, and then we can see the change. And so we just need to know that pressure and volume have a seesaw relationship or an inverse relationship, but volume and temperature and pressure and temperature both have a direct relationship. Okay, so those were our notes, and those were on page 105. Now we're going to be working on page 104 for maternity leave. Your homework is 237 through 247, and that's in the textbook appendix. So if you look and find our textbook, and you flip to the very, very back of the textbook, page 115, gas laws, and we're looking at these problems. Okay, to make it easier, I've written a couple of the problems out for us, and I'm going to do these as examples to make sure that we're successful with the gas laws. As a reminder, these are our equations, and so I'm just going to stick them up here, and we will choose from the equations as we're doing the problems. And so let me just make sure that we are still on screen, and we should be able to see and solve. Okay, so we're going to be using your algebra skills, and we're going to have to know how to manipulate an equation for the variable that we're missing. So I'm going to look at problem 237A, and it's a chart, and you're going to fill in the chart, but we're just looking at the first one for this example problem. So they've given us a pressure and a volume initially, those are my ones, and then the pressure changed. We have a P2, and I want to know what the second volume is. So I know I'm going to be using this equation because I have two pressures and two volumes. I check and make sure my pressure units are matching. They're both in ATMs, so that's going to be fine. I don't have to do anything funny for that. I don't have to do any conversions. Okay, so I'm going to go ahead and write P1 V1 equals P2 V2. I know that I am solving for V2. So I'm going to go ahead and circle V2, and I need to isolate it, get it by itself. Well, it's currently being multiplied by P2, so I'm just going to divide both sides by P2, and I'll get my equation. So my volume is going to equal the pressure and volume of my initial conditions divided by the change in pressure. So all I have to do now is plug those numbers in. So I have 3.0 ATMs for pressure 1. I have 25 milliliters for volume 1 divided by 6 ATMs for pressure 1. Now we'll notice that my ATMs cancel, and so all I have to do is multiply and divide. So I take my calculator and I say 3 times 25 divided by 6, and I get an answer of 12.5. I have 2 sig figs, 12.5. I only have 2 sig figs, so I'm going to round that to 13 milliliters, and that would be my answer for 237A. plugged it in, manipulated the equation, solved. Okay, so now let's look at it as in terms of a word problem. Our second problem that we're going to do is 238. And 238 says a sample of neon gas occupies a volume of 2.8 liters at 1.8 atm. And what will its volume be at 1.2 atm? So I can see that the pressure is changing. So one of the things that helps me is just to go in and label them. I know that initially I'm starting out at this volume at this temperature. At is a really important word. It connects to values. So I know that they're going to be on the same side of the equation. So this is my initial volume and my initial pressure. What will its volume be at 1.2? Well, that's changed. So that's going to be my second pressure. I notice that my pressure units are matching, so I don't have to convert. So I'm going to set up my equation, P1V1 equals P2V2, because I'm dealing with just pressure and volume. So I'm going to use my first equation here. Okay, what will its volume be? So that's like a new situation. So that's going to be V2 that I'm looking for. So again, I'm going to do the same thing that I did before. I'm going to circle V2 and isolate it, which means I need to divide by P2 on both sides. So V2 is going to equal P1 V1 over P2. Now I have to say that just randomly as selected the problems, this is what I was looking for. But you can look for any of the variables. You just have to make sure that if it says at, you're connecting those terms and they end up on the same side of the equation. And then for this type of problem, you'll just divide by the other number that they give you. Okay, so we're going to plug those numbers in. So our first pressure, and it may help some of you to write out a list. And so I'm going to write out a list kind of like they did in the chart because it just helps our eyes. So we know that our initial pressure was 1.2 atm. Our initial volume was 2.8 liters. Our second pressure was 1.2 atm, and we were looking for our second volume. Okay, so let's take that and let's plug that into our equation. So initial pressure was 1.8 atms times our initial volume of 2.8 liters divided by our final pressure of 1.2 atms. So I'm going to plug that into the calculator. 1.8 times 2.8 divided by 1.2 atms gives me 4.2. 4.2, and since my ATM's canceled, I'm left with liters. Okay, it's important that I can justify my problems. And so I'm going to go back and look at 237A for a second and show how I know this makes sense. Okay, the pressure went from 3 to 6. So if I'm thinking about this, the temperature is constant, the pressure went up from 3 to 6. So the volume should go down. My initial volume was 25, now it's 13, so it matched what I thought should happen. It's an inverse relationship. When the pressure went up, the volume went down. So let's look at my second situation. In my second situation, which temperature was constant, my initial pressure was 1.8 and it went down to 1.2. So since the pressure went down, the volume should go up. My initial volume was 2.8, my final volume is 4.2, so yes, it went up. The pressure went down, so the volume should go up because pressure and volume have an inverse relationship. Okay, let's look at problem 242. In problem 242, they tell us that we have a volume of 40 milliliters, a temperature of 280 K. That's important that it's in Kelvin, so I don't have to convert. I'm looking for a second volume in milliliters, and my temperature 2 is in 350 K. Okay, these problems are a little bit trickier because some people have trouble with the rearranging the equation. But I know that I have volume and temperature, so I'm going to be using V1 over T1 equals V2 over T2. And I'm looking for the second volume. So I'm going to circle the second volume. Okay. There are two ways to solve this. There's cross multiply and divide, which is the way that I prefer. But there's also where you can multiply both sides by the denominator. So I'll show you both ways. I just do cross multiply and divide. So that means that I would take V1 times T2 and divide it by T1, and that would give me V2. That's just cross multiply and divide. But some students need to see this rearranged, and so I'm just going to show you that I could, since this is being divided, I could say that I'm multiplying both sides by T2 and end up with T2 times V1 over T1, which is the same thing. So you can either just do cross multiply and divide, or you can solve it algebraically and you'll end up with the same equation. V1 times T2 over T1 equals V2. Okay, so we just need to plug in our numbers. Our initial volume was 40 milliliters. And so we probably need to make a list. Let's see here. So, well, we don't need a list because we've got it right there. Our initial volume was 40 milliliters. Our second temperature was 350 K. And we're going to be dividing that by our first temperature, which was 280 K. And so when I plug that into the calculator, 40 times 350 divided by 280 gives me 50 milliliters. 50 milliliters. And we'll put a decimal point at the end of that so we get our 2 sig figs. Okay, so let's make sure that this makes sense. We're going to use our little sticky note. Our temperature went from 280 to 350, and so we know that we're keeping pressure constant. So our temperature went up, which means our volume should also go up. It was 40, now it's 50. So yes, temperature increased, so the volume should increase. All right, let's look at it in a word problem. A sample of argon has a volume of 43 milliliters at 24 degrees Celsius. That at tells me that these two numbers are connected. This is my first volume, and this is my first temperature. Now I notice that it's in Celsius, so I'm going to have to deal with that. At what temperature in Celsius will it have a volume of 0.57 milliliters? Well, that's a change. So this is going to be volume 2, and so I must be looking for temperature 2. Now notice that it says it wants it in Celsius. That doesn't matter that it wants it in Celsius. We must do our temperature conversion to Kelvin first. Okay, so I'm going to make a little list of our conditions, and then we'll play this out. So we know that our first volume is 0.43 milliliters, and our first temperature is 24 degrees Celsius. I'm going to go ahead and deal with that and add 273 so that I get 297 Kelvin. Okay, got to make that in Kelvin. And then my volume 2 is 0.57 milliliters, and I'm looking for my second temperature, but I want to get it to Celsius. I'm going to have to do it in Kelvin first. Okay, so when I write down my equation, V1 over T1 equals V2 over T2, I'm going to be solving for my second temperature. Okay, so that's the one I'm looking for, my second temperature. Again, you can just cross multiply and divide, or you can rearrange the equation. You would have to take the reciprocal of each of these, multiply each side by the reciprocal in order to get this to do what we need to do. So we can do that. T2 over V2, and then, we would be able to solve. But I'm just going to cross multiply and divide. So I'm going to take T1 times V2 and divide it by V1. And that'll give me T2. Okay, so we're going to plug in our numbers. I guess I need to plug those in first. So our first temperature was 297 K, because it had to be in Kelvin. Our second volume was 0.57 milliliters divided by our initial volume of 0.43 milliliters. My milliliters cancel, and so I take 297 times 0.57 divided by 0.43, and I get 393.6. Kind of running out of space here. Right to the side. 393.6 Kelvin, but they wanted it in Celsius. So I'm going to have to subtract 273 from that. So I'm going to take my answer minus 273, and I get 120.69. It looks like I can have 2 sig figs, so I'm just going to say 120 degrees Celsius would be my final answer. Now, let's see if this makes sense. We can see that our volume went up, so our temperature should also go up, and it did. It was initially 24 degrees Celsius, now it's 121 degrees Celsius. Okay, so let's just take a second and let's make sure that all of those values got where they needed to be. We had temperature 1 of 297, a volume 2 of 0.57, so 297 times 0.57 divided by 0.43, and we get 393. We subtract 273 in order to get 121 degrees Celsius. Or actually, for sig figs, that should just be 120 degrees Celsius for 2 sig figs. Okay, and we made sure that it made sense. Our volume went up, so our temperature should also go up when pressure is constant because they are direct in their relationship. Okay, 2 problems to go. 245A says pressure 1 is 0.15 ATMs. Temperature 1 is 273 K. Pressure 2 is an unknown amount of ATMs, and temperature 2 is 410. Okay, so again, we know now that we've got pressure and temperature, so we're going to be looking at this equation. Okay, so we're going to use P1 over T1 equals P2 over T2, and we are solving for our pressure. Okay, so in order to solve for our pressure, we can cross multiply and divide, or we can multiply both sides by T2 in order to solve. And so pressure 2 equals pressure 1 times temperature 2 divided by temperature 1. Okay, so let's plug in our numbers. For pressure 1, we have 1.50 ATMs times temperature 2, which is 410 K. It's in Kelvin, so I didn't have to convert, divided by temperature 1, which was 273 Kelvin. And so when I plug that into the calculator, 1.50 times 410 divided by 273 equals 2.25. Equals 2.25. I can have, I think there's a decimal point at the end of this, so I can have 3 sig figs, so we'll leave it with 2.25. My K's cancel, so I'm left with ATM. So I get 2.25 ATM. All right, so let's see if that made sense according to my problem. My pressure is what I'm looking for. My temperature went up. So my pressure, according to my sticky note, if my volume is constant and my temperature goes up, my pressure should also go up. My pressure initially was 1.5. It ended up being 2.25, so the temperature went up, the pressure went up. That's a justified answer. Okay, last question. And I'm going to kind of shift this up so we have a better view of it. All right, so in our last question, we're going to look at question 246. And question 246 says a cylinder of compressed gas has a pressure of 4.822 ATMs on one day, on the first day of the experiment. The next day, the same cylinder of gas has a pressure of 4.69 ATM, and the temperature is 8 degrees Celsius. What was the temperature of the gas on day 1 in Celsius? So I'm going to make my little list. I know that we're talking about pressure and we're talking about temperature. So I'm going to have pressure and temperature on day 1 and pressure and temperature on day 2. Okay, so I know that the pressure on day 1 is 4.882 ATMs, but I don't see any mention of the temperature on day 1. They're actually asking me for that. So that's going to be my variable. I know the pressure on day 2 was 4.690 ATMs, and we see that keyword "and" connecting them. The temperature is 8 degrees Celsius. So I'm going to go ahead and add 273 to that, so I get 281 K, because I know that my temperatures have to be in K. All right, so I'm going to be looking for T1. So that means that I must be doing this equation. Okay, so I'm going to take P1 over T1 equals P2 over T2, and I'm going to be solving for my initial temperature. Okay, so I can multiply and divide to get rid of it, or I can just do cross multiply and divide, which is what I prefer. So I'm going to take P1 times T2, P1 times T2, and I'm going to divide it by P2, and that'll give me T1. Cross multiply and divide. Okay, so let's plug in our values for that. P1 is 4.882 ATMs, but T2 was 281 Kelvin. And I'm going to divide that by my second pressure, which was 4.690 ATMs on day 2. My ATMs cancel, and so when I type that into the calculator, 4.882 times 281 divided by 4.690 gives me 292.5 equals 292.5 Kelvin. Now, it asked for it in degrees Celsius. So I'm going to subtract 273 from that. So I'm going to take this and subtract 273, and I get 19.5 degrees Celsius, which I actually only get 1 sig fig, so 20 degrees Celsius. Let's see whether or not that makes sense and whether or not it follows the pattern. Our pressure went down, so our pressure goes down, our temperature should also go down. And so if our temperature didn't go down, we may have an issue within our problem. And so let's check this again and let's make sure we've got everything that should happen. Oh, actually, I'm sorry. We've got to kind of work in reverse. So our pressure went down from P1 to P2. So our temperature should be higher on day 1 than it is on day 2. And that is true. Temperature on day 1 would be 20 degrees Celsius. Temperature on day 2 would be 8 degrees Celsius. We kind of worked this problem in reverse, so we kind of would have to say that in comparing them, the pressure went up in looking at it in reverse, but we're not. If we look at day 1 to day 2, the pressure goes down, so the temperature should start at 20 and then go down to 8, and it does, because if the pressure goes down, the temperature is also going down. Okay, so that was textbook appendix problems from page R115, and we were looking at the gas law problems, and so we looked at problems 237A, 238, 242A, 244, 245A, 246. We reminded ourselves that we had to manipulate the equation for the missing variable, and our temperatures were always in Kelvin. Even if they asked for it in Celsius, we had to do the problem in Kelvin. Okay, so I hope this was helpful to you. Now you can get to work on the rest of the problems.